Hey everybody on YouTube, I want to talk a little bit more about simplex tableaus. So far we've been doing a bunch of examples, and quite frankly, I think that's a fantastic way to learn. But I want to show you some of the notation that people use when talking about the simplex method in general, mainly just so that you recognize it. And if you want to learn more, you're not scared of this notation, you can bite in and chew it and digest it and understand it. So we're working on linear programs in equational form. So all of our constraints are equality constraints, except for the non-negativity ones. And C transpose X, that's the function we're trying to maximize. And we're going to call that the variable Z. Okay. Matrix A is of size m by n. And that just tells you that we have n variables, x1 up through xn. And then we have m equations in our equality constraints. So an important definition for this class is, what is a feasible basis? A feasible basis, well, you have to choose m of your n columns in A. Okay, so a subset of m columns out of all n columns. And once you choose those columns, when you restrict attention to those columns, the resulting square m by m matrix you get is supposed to be non-singular, so non-zero determinant. Okay, and there's one other thing we need. The unique solution that you get to solving this has to be non-negative. All right, so let me talk about that a little bit more. So pretend here is our linear program in equational form. Here's the matrix A. Let's try to choose this, this basis B to be the columns 3, 4, and 5. Okay, so when I do that, AB is the matrix that I get when I restrict to those columns. So I get this matrix, which is indeed non-singular. Okay, and then XB, what is XB? XB is just take that vector X and restrict it to the third, fourth, and fifth entries. The entries in our basis B, right? X is X1 up through X5, but XB is just restricting to the entries in my basis. This matrix is non-singular, so when I solve this equation, I get a unique solution XB. So in this particular example, I take this square matrix, I multiply it by the vector x3, x4, x5, and it's supposed to equal 1, 3, 2. So it's pretty easy on this example to solve for x3, x4, and x5. They had better be 1, 3, and 2, because AB was the identity matrix. Okay, and so another property in basic feasible solutions is we better have that all the entries in XB are non-negative, right? Because otherwise you're not a feasible solution. Questions so far? All right. So here's our notation. It's a lot of notation, but then I want to try to start explaining it. The simplex tableau determined by a feasible basis is, well, we can write our basic variables as some vector plus some matrix times our non-basic variables. And then our optimization function is equal to some constant plus some linear combination of our non-basic variables. So we've expressed our basic variables and our optimization function in terms of the non-basic variables. the non-basic variables, to have a basic feasible solution, you always have to plug in 0 for the non-basic variables. But here we're thinking of these as variables, and so we have a system of equalities, linear equalities. XB will be the vector of basic variables. N is going to be the indices of the non-basic variables. So in the example up above, N is going to be the remaining variables 1 and 2 that are not in my basis. All right, I've already said Xn is the vector of non-basic variables. P is a vector with n rows in it, m rows in it for m different equations. This vector has length n minus m, and so R also has to have length n minus m in order to take this inner product. And you can figure out the size of Q, and Z naught is just a real number. When I plug in 0 for my non-basic variables, Z naught is going to be the current value of my optimization function. Okay, hopefully you're all very mad at me and angry and confused and sad, and this is why you don't like math anymore. And okay, well, let me try to make it a little bit better. So here's an example tableau that we've seen previously in this class. I think before we called this simplex tableau C. We started at A, we moved to vertex B, and then we moved to vertex C. And once we got to C, our non-basic variables were 3 and 5. Our basic variables were 1, 2, and 4. And you can see that x1 and x2 have the values 1 and 2. So when I plot this point just in the plane, I am indeed at the point 1, 2. All right, so yeah, our basic variables are these guys. Our non-basic variables are x3 and x5. P is telling you what's your current location, right? So P is telling you the coordinates of your current vertex, 1 and 2, and then the value of x3 is 0 because it's non-basic. The value of x4 is 2, it turns out, and the value of x5 is 0. So just think of P as that tells you the vertex that you're currently at. Z is Z. 3 is where we currently are at in our optimization function. So it turns out, I think on this problem, we're trying to optimize x1 plus x2. And right now, that value is currently 1 plus 2, or 3. And then R is just encoding these coefficients. I have a 1 in front of the x3 and a -2 in front of the x5. So R is just telling you how your optimization function depends on the non-basic variables. Any questions so far? Okay. So here's the fake lemma 5.5.1. You'll see the real lemma 5.5.1 in a moment. There are formulas for all of these terms, Q, P, Z naught, and R, that really only depend on B, your basis, and the matrix AB inverse. Okay, so from B, in this case 3, 4, 5, you get your matrix AB. And then if you invert that matrix, you can get formulas for all of these terms, P, Q, Z naught, and R in your simplex tableau. The real lemma 5.5.1 is you're sort of strictly not allowed to memorize these formulas, okay? So yeah, do not memorize those formulas. I don't think they matter. The point is that they exist and they depend on your choice of B, your basis, and on this matrix AB inverse. Okay. So let's prove this fake lemma just to feel like we did a little math today. I've copied down here below the general notation for our simplex tableau. Okay, so this is just copied and pasted from above. And I just want to show you quickly how to derive these formulas so that hopefully you're not as so scared of them. All right, so a times x equals b. You know, matrix A has n columns and vector x has n rows, right? But you can write that as only look at the columns in my basis times the corresponding coefficients in my vector x, and then only look at the columns not in my basis times the corresponding basis x. So so let me draw this a little bit more. I'll come back, but let me go up here. So pretend my basis is 3, 4, 5. You can imagine what matrix A times vector x is. But another way to write that is you could write AB times XB plus AN times XN, which is matrix AB is just this identity matrix times X1, X2, X3. And then matrix AN is just the first two columns times X1, X2. And that is indeed equal to A times X. I'll sort of cheat. That's indeed equal to this.
Henry,
Yeah.
in that first, when you're writing the concrete example on the first one, do you mean x3, x4, x5?
Yeah, what did I put?
1, 2, 3.
You were right. Thank you. That's the worst. When you do a concrete example and you get it wrong, right? It's better just to not be concrete. All right. So, I mean, you can check that this side, if you multiply it out, is equal to this side. Okay, but the reason why you should believe me is this is on the left. I just have x1 times this first column, x2 times the second column, x3 times the third column, plus x4 times the fourth column, etc. And that's exactly what I have on the right-hand side. I have x3 times this column, x4 times that column, x5 times this fifth column, and x1 times the first column, etc. Other questions there? My board work was not so beautiful today. But... All right, so that's where this equation is coming from. So we can write this as a sub b times xb is equal to the vector b minus an xn. I've just subtracted an xn from both sides. And now ab is invertible, so I can solve for this vector xb. It's ab inverse times this right-hand side, b minus an xn. Okay, so we have already proven part of our lemma. Let's see. All right, wait. Can't see it right now. Oh, right, okay. So we've proven these two parts of our lemma. We've proven what Q is, and we've proven what P is, okay? And so Q and P appear here. You can write your basic variables XB in terms of P and Q. P is sort of the constant vector in that equation, and Q is the matrix that you multiply by the non-basic variables, okay? So this right here is giving us P and Q. P is just this constant part, AB inverse times B. Okay, so that's where P is coming from. And then Q is the matrix that you multiply your non-basic variables by. So Q is AB inverse, negative AB inverse times AN, right? So that's why Q is negative AB inverse times AN. You with me? Okay. Sort of have to like see through the notation somehow. And now in what follows, we're gonna solve for Z naught and R. Z is what we're trying to optimize, C transpose X. You can write that in a very analogous way to what we did here as the inner product of the variables that are basic plus the inner product of the variables that are non-basic. Okay, so I think of this as the inner product of all variables in C and X is the inner product of the basic ones plus the non-basic ones. And now we're going to take XB and plug it in right there. So this is just CB transpose times AB inverse times B minus AN XN. All right, and then in this last step, to get down to this equality, we're going to pull out the XN parts. So think of XN as our like common variable. So I have CN transpose copies of XN, but then I furthermore have minus CB transpose times AB inverse times AN XN, giving me this bit. Right. And then after I've separated out the XN part, what remains is just CB transpose times AB inverse times B. All right. So you'll remember where our Z naught and R coming from. Z is equal to Z naught plus the inner product of R with our non-basic variables. And I've written Z as some constant. So that's the Z naught plus some inner product of this basic, or this vector with our non-basic variables. So this is R. The two things that are highlighted in green right now, one is just the transpose of each other. They're the same vector. One is just transposed. All right, so cool. We did some real math. These formulas exist. The main point is that you can always find them after you've chosen a basis and you just solve for this matrix AB inverse. Any questions?
I have a quick question.
Yeah.
Mainly, I think because I missed the last couple of lectures and I haven't got caught up yet. But
no worries.
The non-basic solution or variables, the ANs, those are
XNs, I would say.
Oh, sorry, yeah, XNs. Those are those our can we think about those as our added what's the right word? Basically, we have a solution that has 3 variables, but then we have slack variables essentially for. Or I guess what do the XN or the XNs represent?
Sure. Yeah. So oftentimes, but not always, when you have well, yeah, let me be more specific. When you have a linear program where all of the equations at first are less than or equal to's, right? Then you add in slack variables, right, to put it in equational form. And when you add in slack variables, you can always choose your slack variables to be your initial basic variables. And so then your initial non-basic variables are the leftovers that are not the slack ones. But that's only usually when you start, right? So the slack variables sometimes give you a way to choose your basic and non-basic solutions at the start. I mean, how you want to think about it is you have some starting basis, which gives you a starting vertex. and then you change basis and you get a different vertex. You change basis, you travel along an edge to a different vertex, and you keep going until you can no longer improve.
Okay.
So we can talk further, Patrick. I think there's more to say there.
Cool, thanks.
All right. So now that I've introduced you to this notation, P, Q, Z naught, and R, I just want to say a few comments using this notation. Remember what P corresponds to, what Z naught corresponds to, and R corresponds to these coefficients. Q corresponds to these coefficients. So if R is non-positive, if none of these coefficients are positive, then you can't improve your optimization function Z by increasing any of your non-basic variables. So if R is non-positive, then the corresponding basic feasible solution is optimal. You're done. You've solved the problem. And then let's say I was about to pivot. Let's say I wanted to do better. Would I increase x3 or would I increase x5? I would increase x3, right? Because I want Z to get bigger. X3 and x5 are both currently 0, so I would increase x3. So a non-basic variable, such as x3 here, may enter the basis. You can pivot and add it to the basis if and only if its coefficient in this vector R is positive. Okay. You could pivot and add in x3. You would never pivot and add in x5 because then you'd just be making backwards progress. P, Q, Z naught, R, those are just names. But this notation comes up a whole lot when people talk about the simplex method. When you pivot, so let's say we add in x3, you need to find your variable that leaves. So if we pivot to add in x3, some other variable is going to leave. And what is the variable that leaves here? So from the perspective of this first equation, I can increase x3 as much as I want. Same from the perspective of the second equation. But from the perspective of the third equation, this equation for x4, I can't let x3 get any bigger than 2, right? So x4 is my limiting variable. It's going to be the variable that leaves the basis. So this is notation for how you choose the variable that leaves the basis. This QUV is supposed to be one of the entries of this matrix. And for x4 to be the variable that leaves the basis, you need this coefficient here to be negative, right? So this is a -1 here, that entry of that matrix Q. And furthermore, you need, well, let's see. So how much can we increase x3 by? We can increase x3 by 2. And how did I solve for 2? I took this entry of the vector P. Remember, here's the vector P. I took this entry of the vector P, I made it negative, -2, and then I divided by this entry -1, okay? So that's solving for how much I can increase x3 by 2, but in other words, -2 divided by -1, okay? So your leaving variable is going to be the one in which that ratio is minimized over all possible leaving variables. In this example, there's a unique minimum, right? x4 is the only leaving variable that minimizes this set with value 2 in this case. In general, though, you could have multiple different possible leaving variables, right? We choose x3 to enter. Maybe x4 and x17 both minimize this set. So you need rules for choosing when there's more than one entering variable that you could use or more than one leaving variable. Which one do you choose? The choice of entering variable matters a lot. the choice of leaving variable is not quite as important. All right, so that's all I wanted to say about the simplex Tableau and using the more general notation. Any questions? Thanks.